Hello everyone. So we'll continue from exactly where we left off in the previous lecture. We were about to substitute the expressions of epsilon xx, epsilon yy and epsilon xy from, uh, from the previous page where we had obtained the simplified versions in terms of the sigma xx and the sigma yy after eliminating the sigma zz using this relation. Uh, So we'll do that right away. So del square del y square epsilon xx. You see here epsilon xx contains the 1 plus nu by e, and that is a constant that may come out of this second order derivative with respect to y. We'll have 1 plus nu by e sitting outside, del square del y square, and the rest of it, whatever is inside, 1 minus nu sigma xx minus nu sigma yy. Right, so let me just write that a little bit better. Okay, similarly for epsilon yy we use this relation here from the previous page. Again the 1 plus nu by e goes outside, and we have del square del x square 1 minus nu sigma yy minus nu sigma xx. And on the right hand side I have for my epsilon xy this expression in terms of sigma xy. Again the 1 plus nu by e comes outside of the second order derivative, del square del x del y of sigma xy this time. Now you see that on in each of the terms this 1 plus nu by e is common, so that can be cancelled out, and what we have left, so here this 1 minus nu sigma xx, what we'll do is we will so this is associated with a del square del y square. Now what we want to do is introduce another term involving the sigma xx, but which will have a derivative, a second order derivative with respect to x. So if we do that, okay, so and with the same coefficient 1 minus nu, so what we basically want to do is add a 1 minus nu del square sigma xx del x square, and we also want to subtract that out. Okay, so let's see what happens if we do that. Okay, so from this one, from this first term, what we'll obtain is del square del x square plus del square del y square. Okay, getting this Laplacian out, that is the motivation of introducing a term like 1 minus nu del square sigma xx del x square. So we get that. Now let us write whatever is remaining in this one. Okay, so let's write that. We are not manipulating that term, let it remain as it is. Now just like we had manipulated this one, let us manipulate this one also. Now what we are going to add this time is 1 plus nu del square sigma yy del y square, because our motivation is to obtain a Laplacian term. So when we do that, we obtain del square del x square plus del square del y square operating on sigma yy, and we write this remaining term as it is. However, we are far from done, because we have not yet adjusted the artificial adding of this term, so we need to subtract that out. Now it is adjusted. this artificial addition of this term, that is adjusted by this term. Similarly, we had artificially added this 1 plus 1 minus nu times del square sigma y del y square, and we need to subtract that out also. Now we are done on the left hand side. On the right hand side, what we'll have is this del square sigma xy del x del y. All right, now let's see if we can have any simplification. You note this term has a minus nu, and this is a similar sort of term in terms of the second order derivative with respect to y, but it has basically a plus nu sitting in front. So what will basically remain from here is a minus del square sigma y del y square. Now let us consider next this term along with this term. Here we have a minus nu del square sigma xx del x square, but here we have a plus nu del square sigma xx del x square. So overall, this gets substantially simplified. Now in this next step, we are actually going to write this one as a Laplacian of sigma xx and this as a Laplacian of sigma xx. So overall, that 1 minus nu times the Laplacian, that gets taken as common. So overall, we have this nice compact term from here and from here. This one, as I said, this gets simplified over here and this gets simplified over here. So what we have basically is minus del square sigma xx del x square, and from here we have minus del square sigma y del y square. That is equal to del square sigma xy del x del y. I think I missed this 2 here, so that should go here and that should go here. All right, now just as I had been proceeding earlier by numbering the equations, let me do that also here. Otherwise it's going to be a jumbled mess to refer to it once we have more number of equations. So let me call this, so since we are continuing in the same document, let me just take a look at the last numbered equation. So we had this as 10. Let's say and this as 12, so let's say this is 13, and let's say this biharmonic equation, that is our equation number 14. Similarly, let's say this is our equation. Actually, I would like to start the numbering all over again, otherwise it's going to be a huge, a very large number in the equation number. So if you don't mind, even though I'm working in the same document and can do this, but I don't need to number this one. Let me call this as my number 1 equation here, this as my number 2, this will be number 3, this is number 4. I don't need these two, and what I'm basically doing here is so this is my equation number 5. In order to obtain these equations, this term, what I'm doing is to use equation 1, equation 2, equation 1, 2, and equation 4 in equation 5. That's what I did. Okay, so after I've obtained this, what I'll say is that this is my equation number 6. All right, now I'm happy. Now, just like as I had proceeded in the case of the plane stress paradigm, what I will do, in order to simplify these equations and also to take into account the stress equilibrium equations, I considered these two equations, uh, or uh, these stress equilibrium equations, but considering the body force terms. Okay, so here, just for the sake of discussing it as a side note, I had not considered the body force term, but this time I will. Okay, so uh, let me quickly go to the next page and consider the equation with the body force term. Please note that I am no longer, on the basis of that earlier discussion, I am no longer writing the stress components involving the Z. Now, my motivation is to somehow arrive at terms involving the second order derivatives of sigma xx and sigma yy with x and y respectively. So I differentiate this first one just like as I had done in the case of the plane stress formulation with respect to x. So I obtain del square sigma xx del x square plus del square sigma xy del x del y, and that is minus of del fx del x. The second one, I differentiate with respect to y so that I obtain del square sigma xy del y del x plus del square sigma yy del y square, that is equal to minus del fy del y. So let's call these two equations equation number 7 and 8. And again, I add up 7 and 8 to obtain del square sigma xx del x square plus del square sigma yy del y square, plus I add these two together because again the continuity of second order derivatives, so the order of the derivatives do not matter. Del square sigma xy del x del y, that is equal to minus of del fx del x plus del fy del y. Alright, so let's call this equation 9. Now I want to use equation 9 back in my equation number 6. Okay, so this term remains as it is, and I'm going to substitute this particular expression from this equation number 9. So use 9 in 6. So this is 1 minus nu del square sigma xx plus sigma yy this one. I take the minus common, and this is, so if I just go back here and write like this, so whatever is within the bracket, that can be written from equation number 9 like this. Sorry, on the right hand side I do not have a 0, rather I have this term involving the sigma xy, twice del square sigma xy del x del y. So what I obtain from here, if you note that this minus and this minus is a plus, so this term is cancelling with this. So overall what I'm going to get is this 1 minus nu Laplacian of sigma xx plus sigma yy, that is equal to, so this minus and this minus is a plus on the left hand side. If I transpose these two terms on the right hand side, I will get minus of, within bracket, del fx del x plus del fy del y. Okay, now let's call this equation number 10. Now this is the point, uh, uh, this is the corresponding in the plane stress condition, and the plane stress formulation. At this corresponding point, what we had done was to introduce the eddy stress function. Okay, so we'll do that again by considering the stress equilibrium equations again. So we go back to these two equations and consider them again. So consider the stress equilibrium equations again. We consider them again, but with conservative body forces. So just like in the case of the plane stress. And when we have conservative body forces, they can be written in terms of a scalar potential. So what we basically have is uh, this fx term being written in terms of a minus del p del x. So we can write this fx as a minus del p del x, so that what we basically have is this del x of sigma xx minus of uh, v, sigma xx minus v, plus del sigma xy del y is equal to 0. And similarly from the second of the stress equilibrium equations, we have this minus del v del y term, so that overall this can be written as del sigma xy del x plus del y of sigma yy minus v equal to 0. Now these two equations, okay, without going into any more detailed discussions, these based on what we have already discussed, it's exactly the same way, the same logic. So these two equations will be identically satisfied, okay, if we use sigma xx minus v is equal to del square phi del y square, sigma yy minus v is equal to del square phi del x square, and sigma xy is equal to minus del square phi del x del y. I repeat, when we use these particular forms back here, these two equations are identically satisfied. So if we can use these equations back in equation number 10, okay, so use in equation number 10. So what we obtain then? So we come here and look at it, 1 minus nu del square v plus del square phi del y square plus v plus del square phi del x square. This is from sigma xx, and these two are from sigma yy. So on the right hand side we have the minus of del fx del x. So that fx will be substituted by minus del v del x. So overall we have a del square v del x square, and here we'll have a del square v del y square. So and please note here that this is a twice v. So this is 2 into 1 minus nu del square v plus 1 minus nu, and this is a Laplacian, but there is already a Laplacian outside. We have to take care of that. On the right hand side, this is simply the Laplacian of V. Okay, so if we go to the next page, we just have to take care of taking this thing appropriately to the right hand side, and what we'll obtain is this. So this one remains as it is. This 1 minus nu, we have the biharmonic operator appearing again, and this is 1 minus 2, because this is a 2 here, and this minus 2 nu becomes a plus 2 nu, and we have this Laplacian of V. So what we have basically is this del 4 phi is equal to minus 1 minus twice nu divided by 1 minus nu del square V. So this final form of the plane strain formulation, let us compare this quickly with what we obtained at the end of the plane stress formulation. If we go back a few pages, we'll see that this final equation, the biharmonic of phi, the biharmonic operator operating on phi, that is equal to minus of 1 minus nu del square V. Okay, so and now everything is the same except this coefficient. Okay, so this is from the plane strain formulation. Let us not forget that. Okay, and what we had obtained earlier for plane stress, we had obtained del 4 phi is equal to minus of 1 minus nu del square V. So again, this equation number 13 on the previous page. All right, so just like as we had talked about the special case that when body forces vanish, or del square V is equal to 0, then we simply have the biharmonic equation. Okay, so this is true for plane strain as it was for plane stress. Okay, so this should tell us the great importance of this biharmonic equation. Okay, and it is based on this that we are going to solve a lot of the problems. So with this we end this part of the lecture, and we'll see various ways in which we can proceed towards the solution of this biharmonic equation in the subsequent lectures. All right, thank you very much.